We've had reports that have come out talking about the fact that we only have maybe a dozen programs in the country that are capable of producing people with training in radiochemistry. So Texas A&M, we're looking at building upon the strength of our existing nuclear science research programs in nuclear engineering, our reactor-based research, our cyclotron-based research. And so we're looking at expanding radiochemistry into making that something as well. And so what we've done is we have a project funded by the DNDO, which is part of the Department of Homeland Security. As part of that, we've been studying the chemical characterization of spent nuclear fuel and trying to determine what types of reactors produce that different type of fuel, for example. So it involves bringing in students with experience in nuclear engineering, brings in students with experience in chemistry, and then working together to solve these problems and hopefully help this issue of promoting the pipeline of trained radiochemists in the United States.
Overall objective of this project, funded by Domestic Nuclear Detection Office, is to find out if an adversary brings in or smuggles in plutonium, specifically the nuclear material used in weapons. If they try to smuggle in to the United States of America, we would like to see what was the source of this special nuclear material, plutonium produced. Specifically with respect to what type of reactor would have produced this material. And if we know the type of the reactor, then we can do the process of elimination with respect to different countries, and we can probably nail down to a couple of countries who are the producers of this type of nuclear material, specifically plutonium. The first thing we do is to do computationally find out how much plutonium and what type of trace contaminants will go with plutonium when we try to separate. So that's the computational work, and then we validate the computational work by doing experimental irradiations of uranium dioxide surrogates in different reactor spectrum, like fast reactor spectrum and thermal reactor spectrum. And then we compare the computational values with the experimental values so that we can confidently say with some % of uncertainty, this particular plutonium would have come from this particular type of reactor.
So the main objective of this work is to look at separated weapons-grade plutonium and attribute that to its source reactor. And so we do that by computationally simulating and modeling multiple reactors. And we look at the plutonium coming out of it. And once we are looking at the plutonium, we then also think about the fission products that are going to be contaminants in this plutonium. And for our work specifically, some of the fission products that have been useful are going to be cesium and samarium-150. Isotopes like that, which are going to be affected based on the neutron spectrum of the reactor and the certain type of reactor. And so looking at those isotopes of our separated plutonium, we can say it probably came from certain types of reactors.
Over here, we're using this glove box with an inert atmosphere to do our chemical separation processes. We're also using this lead glass and bricks to reduce the dose that we're receiving, which is already below the permissible limit. We're just wanting to ensure that we're having reduced doses. One of the issues that we see with spent fuel is the filtration process to ensure that there's not a release of radionuclides to the environment. In this case, our glove box has a dedicated filter, two filter, with one being a HEPA and one being a charcoal filter to capture any of those nuclides that could have been aerosolized. In this fume hood, we were looking at doing dry runs for our radiochemistry techniques because we're nuclear engineers and not traditionally trained chemists, so we were wanting to ensure that our manipulations of these processes were correct and we were able to do these separations correctly before we got to the irradiated materials. We were using non-irradiated depleted uranium and stable cerium in these processes. Here we have a sample of natural uranium that we will be irradiating to simulate a CANDU heavy water reactor. The sample is around 20 milligrams, and we're going to be placing it in a reactor to irradiate it.
So the experimental work is very important in validating our computational results. And so the final step in that is going to be measuring the plutonium that has been separated from our spent fuel using our Pyrrhix process. While measuring this plutonium, we're going to be looking at the isotopic contaminants that we saw in our computational results. We use mass spectroscopy and also gamma spectroscopy, which you can see here. This is our HPG, or a high purity germanium detector, and this gives us very sharp, very resolute images of the gamma energies coming out of those isotopic contaminants that are in our plutonium.